The universe is a vast and mysterious place, with countless galaxies, stars, and celestial bodies scattered across an ever-expanding cosmos. But what if I told you that the very fabric of space itself, the universe we live in, may be harboring one of the greatest scientific mysteries of our time? Something that could completely change the way we think about the universe's expansion. This is not a fictional tale, this is the Hubble tension, one of the most perplexing phenomena in modern astronomy. It's a puzzle that has confounded scientists for years and has even shaken the foundations of our understanding of cosmology. At its core, the Hubble tension involves the speed at which the universe is expanding, but it's much more complicated than simply measuring a rate of expansion. If you've ever looked up at the night sky and wondered how fast the universe is expanding, or if you've ever been curious about how the galaxies are moving away from each other, you're not alone. The universe has been growing ever since the Big Bang, approximately 13.8 billion years ago. The expansion of the universe is one of the fundamental truths of modern cosmology, and yet, the speed at which it is expanding is something that we still don't fully understand. It's a concept that seems simple at first but reveals layers of complexity when you dig into the details. The concept of the Hubble constant, which describes how fast galaxies are receding from one another as the universe expands, should be a straightforward number. But, in reality, it isn't. For decades, scientists have tried to measure the rate at which the universe is expanding, using various methods, from observations of distant galaxies to the study of cosmic microwave background radiation. But despite all these efforts, a glaring inconsistency has appeared in the data, leading to a disagreement in the measured values of the Hubble constant. This discrepancy has become known as the Hubble tension, and it has sparked a wave of new research, theories, and discussions that could fundamentally alter our understanding of the universe itself. So, how did this all come about? How is it that a value that was once thought to be fixed and well understood has now become a subject of intense debate? At the heart of the Hubble tension lies the measurement of the Hubble constant. This number, named after the American astronomer Edwin Hubble, tells us how quickly the universe is expanding by relating the velocity of galaxies to their distance from us. When astronomers observe galaxies, they see that galaxies farther away from us are moving away faster, a phenomenon known as cosmic redshift. This relationship was first observed by Hubble in the early 20th century, and it laid the groundwork for the modern understanding of an expanding universe. The Hubble constant describes the speed at which that expansion occurs. However, there's a significant problem. The rate of expansion we observe in the distant universe doesn't match up with the rate predicted by current cosmological models, creating the infamous Hubble tension. The first method scientists used to calculate the Hubble constant was by studying the cosmic microwave background, CMB, radiation, which is the faint afterglow of the Big Bang. The CMB is a relic from the early universe, and it provides a snapshot of the universe's state just 380,000 years after the Big Bang. By observing the CMB and applying our best models of cosmic evolution, scientists can derive the Hubble constant. This method has given us a value of about 67 km per second per megaparsec, km/s/mpc, where a megaparsec is roughly 3.26 million light-years. This means that for every megaparsec of distance, galaxies are moving away from us at a rate of 67 km per second. However, when scientists measure the expansion rate using a completely different method, based on observations of nearby galaxies, supernovae, and Cepheid variable stars, the results don't match up. Cepheid variables are stars that pulse in brightness at a regular rate, and they can be used to measure distances to galaxies. By measuring the distance to these stars and combining that data with the observed redshift of galaxies, astronomers can determine how fast galaxies are receding from us. Using this approach, they have found a higher value for the Hubble constant, around 73 km per second per mpc. This discrepancy between the two measurements, 67 km per second per mpc from the CMB method and 73 km per second per mpc from local measurements, has led to what is now known as the Hubble tension. At first glance, a difference of just 6 km per second might not seem like much. But when you consider the vast distances involved in the universe, this small difference becomes huge. The universe is expanding so quickly that even a tiny change in the rate of expansion can have dramatic consequences for our understanding of its age, size, and overall structure. If we have miscalculated the expansion rate, it could mean that our entire picture of the universe is flawed. The Hubble tension isn't just a theoretical issue, it has real implications for our understanding of the universe's evolution. For example, if the expansion of the universe is happening faster than we thought, it could suggest that the universe is younger than previously estimated. It could also affect our understanding of dark energy, the mysterious force that is thought to be responsible for the accelerated expansion of the universe. The Hubble tension raises the possibility that there may be new physics at play, forces, particles, or phenomena that we haven't yet discovered or fully understood. One potential solution to the Hubble tension involves the idea that the Earth, and, by extension, our entire region of the universe, might be situated in a void. In cosmological terms, a void refers to a large, relatively empty region of space where galaxies and other matter are sparsely distributed. If the Earth is located in such a void, it could explain why we observe galaxies receding from us at a faster rate than we would expect. The Hubble constant would be higher in this underdense region because there is less matter exerting gravitational pull on the galaxies, causing them to move away from us more quickly. This concept was proposed by a team of international researchers who suggest that the Earth is positioned within an underdense bubble in space, surrounded by a higher concentration of matter outside of this bubble. In this scenario, the gravitational forces from the more densely populated regions of the universe would pull galaxies toward the edges of the void, making them appear to be receding from us more rapidly than expected. This could potentially explain the discrepancy in the measurements of the Hubble constant and resolve the Hubble tension. However, this idea is still controversial, and many scientists are skeptical. It also leads to new questions, such as why such voids exist in the first place and whether they should exist according to our current cosmological models. The concept of underdense voids raises another critical issue for cosmology. According to the Standard Model of the Universe, known as the lambda-cold dark matter, lambda CDM, model, matter should be uniformly distributed throughout the universe. This model predicts that the universe is a nearly perfect cosmic smoothie, with matter and energy distributed in a way that is nearly homogeneous across vast distances. However, the discovery of voids in the universe challenges this assumption, as they represent regions where matter is absent or much less concentrated than in other parts of the cosmos. The existence of these voids could require a major revision of our understanding of how the universe is structured on large scales. In light of these issues, some researchers are looking beyond the Standard Model to alternative theories that could explain the Hubble tension. One such theory is modified gravity, which suggests that the force of gravity might behave differently than we currently understand. Modified Newtonian dynamics, MOND, is one such theory that proposes an adjustment to the laws of gravity, particularly in low acceleration environments like the outskirts of galaxies or in the voids between galaxies. According to MOND, the force of gravity at these large scales could be weaker than what we would expect from Einstein's general relativity, which could explain the faster-than-expected expansion rate. MOND has been around for decades and has been proposed as an alternative to dark matter. While the theory has not been widely accepted, it has gained some traction in recent years as scientists look for ways to explain anomalies in the way galaxies rotate and how the universe expands. If MOND is correct, it could resolve the Hubble tension by explaining why we see faster expansion in certain regions of the universe. However, this theory remains controversial, and it is still very much a topic of debate within the scientific community. In addition to MOND, there are other theories that attempt to explain the discrepancy in the Hubble constant. For example, some scientists have suggested that our measurements of distant supernovae and Cepheid variables might be flawed due to factors like dust and gas obscuring the light from these objects. If the light from distant galaxies is dimmed by interstellar dust or other factors, it could lead to an incorrect estimate of their distance, which would, in turn, lead to an inaccurate measurement of the expansion rate. In a recent study, astronomer Wendy Friedman and her team used the James Webb Space Telescope to observe nearby galaxies and their Cepheid variables. They found that when they accounted for the effects of dust and gas, the measurements of the galaxy's distances were more consistent with the predictions from the cosmic microwave background radiation. This could suggest that the discrepancy between the two methods of measuring the Hubble constant is not a result of new physics or cosmological phenomena but rather due to errors in the measurement of distances. While this research is promising, it doesn't completely rule out the possibility of new physics at play. The Hubble tension is a complex and evolving mystery, and we may not yet fully understand the true nature of the universe's expansion. Whether it's due to measurement errors, new particles, modified gravity, or an unknown force, the Hubble tension represents a critical puzzle that could lead to breakthroughs in our understanding of the cosmos. So, what does this all mean for the future of cosmology? It means that we are on the brink of a new era in astronomy, where the very foundations of our knowledge are being questioned and re-evaluated. The mystery of the Hubble tension could lead to profound discoveries that reshape our understanding of the universe itself. Whether it's new theories of gravity, the discovery of unknown particles, or the identification of unseen cosmic structures, the answers to these questions could unlock the secrets of the universe and reveal the true nature of space, time, and expansion. As researchers continue to gather data, refine their models, and explore new theories, one thing is certain: the Hubble tension is not just a scientific anomaly, it's an opportunity for discovery. And we are all along for the ride. The universe is far more mysterious and exciting than we ever imagined, and as we explore these unanswered questions, we may uncover truths that will forever change our place in the cosmos.